Alright everyone, before starting the video I would like to request all of you to join the Discord server given in the description below. We can discuss our doubts or even interact live. And, well, make sure you subscribe to the channel and like the video. Let's jump into it. Hello guys, so today we'll be discussing infinite ladder networks. We'll be discussing them in the context of capacitors as well as resistors. So I'll only explain the approach in the sense of capacitors, but you can also apply the same approach for resistors. So I've picked up these three examples. I'll explain it to you with the help of them. So let's get started. So essentially, in case of infinite ladder networks, what we do is we treat them as infinite expansions for a variable. So for example, if we take x equals to root 6 plus root 6 plus root 6. So it is getting squared again and again. So in this scenario, we are usually taught to approach it in this way. We write it as 6 plus x. Then what we do next is we square both the terms while taking x as greater than -6. And then we get this expression and we solve it by using quadratic equations. So similar to that, we will be approaching it with the same methodology. So like when we write this question down here, we can essentially separate the first chain from the rest of the diagram. So what that leaves us with is this 1, 2, and then a capacitor of C capacitance, and the capacitance of this whole ladder itself is C, right? Because even if we detach it from here, the capacitance is still going to be C because it is an infinite ladder, right? While solving this question in particular, what we are going to do is we'll make the equation of capacitors. So we'll first use, okay, so when we try to simplify this diagram, what we are left with is A, and in parallel to the 1 microfarad capacitor is the 2 microfarad capacitor and the C capacitor. They both are in series, and then we can essentially write them as this. So we'll use the series operator for 2 and C, and then we'll use the parallel operator for 1 and whole of this. So what that leaves us with is 2C upon 2 plus C, and then we'll add 1, and this must be equal to C. When we try to solve the equation, I'll just replace C by X because I'm more comfortable in solving that. So what we are left with then is 2x plus 2 plus x equals to 2x plus x squared. Then we can essentially cancel it out, and x squared minus x minus 2 equals 0. Then we can just solve this equation to get what we are looking for, 2. So C equals 2. Right. We have already figured out that C is also equal to the total capacitance and this capacitance. Now moving on to the next question. This includes the usage of geometric progressions, or if you have studied, then multiplicity of a capacitor. So in this question, what essentially happens is, if you have studied this concept before, what happens is when you multiply each capacitor by 2, then the equivalent capacitance also gets multiplied by 2. Take. Now the reasoning behind it can be analyzed in 2 different ways. So first what we can do is we can take up an example where this is C this is C dash, and so the C equivalent is equal to CC dash upon C plus C dash. Now, if we take up a case where this is 2C and this is 2C prime, then the new equivalent capacitance would be equal to 4cc dash upon 2c plus c dash. Now we can cancel this out and we get this. Now if you take the same case in parallels, the same thing happens. Then we can generalize this result to be true for all operators or all capacitors. Another way to look at it is by dimension analysis. So essentially what's happening is कि C equivalent is nothing, it has no other dimensions than the dimensions of capacitance. So when you are multiplying all things with the dimension of capacitance by 2, then this also gets multiplied by the capacitance of 2. A more elaborate answer to this or explanation to this would be if we take up a square with sides x, 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 and x, and if we try to figure out the area of it, then it would be x squared. Now, the dimensions of it are the square of the dimensions of side, right? So what's happening is when you're multiplying it by a common factor, that common factor is getting squared. But in the case of equivalent capacitance, that is not the case, right? So let's get started with the question and you'll understand it better when you approach it. So we have this ladder with us, right? If the total capacitance of this whole ladder is assumed to be C, and if we remove this portion and this portion, then the total capacitance will become 2C. I just explained why that happened, right? I just explained it via two different methods. You can just rewind the video and watch it again if you didn't understand it. Or I can also share my notes with you. You can just mention that in the comments below. So essentially what's happening is we can redraw it as 1 microfarad and then 2 microfarad and then 2C capacitance, and this all is equal to C equivalent of C only. Okay. Now, when we try to solve this question, we'll just utilize the method we used for the previous case. Okay. So we can just do it 2 times 2C, which is 4C upon 2 plus 2C, which essentially becomes 1 plus C and here 2C. Then we use this, so we add 1 and this all is equal to C, replacing C by X because I'm more comfortable in solving it that way. We get 2x upon 1 plus X plus 1 equals to X. Now when we try to solve it, we get 3x plus 1 upon equals to x plus x squared, which can also be written as x squared minus 2x minus 1. Now when we solve this equation, what we'll get is 2 plus minus root of 4 plus 4, 8. Okay. So you are getting 8. Then it would become root 2 and 1. So 1 plus root 2 should be the answer. This is not quite infinite ladder, but it is a similar type of question. Okay. So it utilizes the same concept. Again, I'll like to mark this as tending to infinity. Then what will happen is all of these are in parallel. Right. So let's calculate for the first branch. The first branch has the capacitance C. Now let's calculate for the second branch. This branch has the capacitance equal to x squared upon 2x, which translates to x by 2. Then the next branch has capacitance equal to x by 4, then x by 8, and so on. So we can see a pattern here. The capacitances are in the pattern of x, x by 2, x by 4, x by 8, x by 16, and so on. So in this scenario, what essentially happens is these are in parallel, so they'll get added. So we are required to find the sum of a GP, and when we try to figure out the sum of this GP, what we get is twice of x. Another way to look at it without using the GP formula is by using this method. So what we do is let's consider this x, then this is x by 2, then this is x by 4, x by 8, and then so on and so forth. So the sum of this whole GP is equals to twice of x, because this is x and this can also be written as x. So you can look at it both ways. You can just visualize it, or you can use the formula for a sum of a GP with a common factor 1 by 2. Both will lead you to the same result, which is then equivalent capacitance is equals to 2 times of C. Well, this is it for today. Thank you.